Hello students, this is 32 and today I discuss about Euler's theorem and homogeneous function, very important differential calculus. So before we start this topic, I wish to appeal all of you, subscribe this channel to get all other videos, and if you like then like this video, and if you like then share with your friends, so must subscribe. So let's start this important topic, Euler's theorem and homogeneous functions. So before we start of this theorem, we have to know what is homogeneous function. The definition of homogeneous function. So first define what is homogeneous function. Any function of two independent variables. Any function of two independent variables. I am taking fx, y, f, x, y. Here x and y both are independent variables, not dependent on each other. So is said to be homogeneous homogeneous. I am not urging that it is independent variables x and y, but it can be dependent also. It can may not be dependent, just variables. F is a function of two variables x and y, and is said to be homogeneous function. In which condition we can say the f is homogeneous function of degree n of function of degree can be expressed if it can be expressed in the form either in this form x to the power n, and another function will get from this function fxy, and this will be in terms of y by x, this form or in this form y to the power n I x by y. So in any one of the term, if it can be expressed among between the two other forms, in any one term it can be expressed the function fxy, two variables x and y, then it is called homogeneous function. I am giving an example to make it easier to understand. Like I am giving a function fxy ax square plus bxy plus cy square. Then we can express it taking x square common. We can express it in this way: a plus b into y by x plus c into y by x. So you can very easily understand that. Now it can be written in this way: x square y. Now it is a function of y by x. Any function also obtained. So here degree is 2. So this is a function of degree 2. It can either express in this way, or we can take y square common and we will get x by y whole square plus b x by y plus c in this form. So either between the two forms you can generate any one form and it will be homogeneous. And given psi x by y. Two forms. Any one form can make the uh, function homogeneous. But we have to carefully note that the function must be reduced, can be expressed in terms of in this form or in this form. Either one of the form, then the function is called homogeneous function. So let's start the Euler's theorem. Euler's theorem said that Euler's theorem, if fxy any homogeneous function, if fxy any homogeneous function, if fxy is a homogeneous function of two variables x and y, then according to the theorem of degree n, this is important, of degree n can be any integer, positive integer, and then we have x into partial derivative of f with respect to x multiply x plus y derivative y into partial derivative of f with respect to y is equal to n into function f. This is a very important Euler's theorem. It have a very good applications in differential calculus especially. So I will go to prove this also. So you can carefully watch that there are two partial derivatives with respect to x and y of the function fxy, and you will get on the right hand side the function also. So here the partial derivatives can be expressed. Any function can be expressed through its partial derivatives. Any function. If the function is homogeneous, then any function can be expressed through its partial derivative. Just if you know the partial derivative of a homogeneous function, then you can very easily of degree and its degree, then you can very easily express it through its partial derivatives. Del f by del x plus y into del x by del y. So in this way, you can very easily express. So it is another topic. Now I prove this Euler's theorem. So it is very simple. Just look. So we have given that fxy is a homogeneous function. So we are late. We can late that fxy. We have two forms. Any one form we can take for fxy. I am taking x to the power n pi. There will be y by x. So now we have two so we have two partial derivatives. We will obtain this del f by del x. So when we differentiate it with respect to x, then we will treat y as a constant. So here is a multiplication of two functions. So we have to use the multiplication theorem or differentiation. So here we will get first x n into del f del and first derivative of phi, first derivative of phi with respect to y by x, and again we have to differentiate y by x. This will be minus 1 by x square. If we differentiate, then it will be y also remain y minus y by x square. If we differentiate y by x with respect to x plus phi y by x n into x to the power n minus 1. Again we will differentiate it with respect to y. Then what will be x del fx? X del f by del x. It will be simply x to the power n plus 1. Here is x square also. So when we multiply with x, then it will be 1 by x also. So it will reduce to 1 by x. Then will be n minus 1. So overall we will get x n minus 1. Also you will get minus. Then you will get y and phi, derivative of phi with respect to y by x. And here you will get n x to the power n multiplying with x and phi y by x. Then again the differences with respect to partial differences with respect to y, we will get now this is a constant with respect to y, and this there y just we can differentiate y. X is constant. There will be x to the power n and phi to the power phi phi derivative of phi y by x. And when we differentiate y by x with respect to y, then we will get 1 by x. So we will get here x to the power n minus 1 x to the power n minus 1 phi, phi derivative of phi y by x. So here if we multiply it with y, if we multiply with it y, then we will get here y and here also y. Then these two terms, this is and this is cut off, cut because they are equal at opposite side. So we will get the right hand side n into the function we have taken fx fxy, we have taken x to y n phi y by x. So we are getting on the right hand side n into fxy. So this is equal to the derivative, partial derivative x into fx. This is the partial derivative with respect to x plus y into the partial derivative of y with respect to y equal to the n number of times of the function. In this way, Euler's theorem can be proved. Easy proofs. And I hope you like this. You have understood and you like this video. Thanks for watching. Thanks for watching.